All right, so we are going to graph what we did in those last two videos. So 0 milliliters of HCl, 10, 25, 50, 60, 75. We're a little bit heavy on the high end. 0 milliliters at all depended on ammonia, 11.08, 86. All right, I don't know what I'm doing here, sorry. 9.86, now that's right. 9.26, 5.36, that was the equivalence point, 2.20, and 1.85. Okay, so now what we want to do is graph this. So insert, let's do a scatter plot. We want this one. This was ammonia with HCl titration. This was our pH, and this was volume of HCl added, and that was in milliliters. Okay, so everything is labeled. All right, so let's take a look at this, and I'm going to change it to red because I feel like it. Okay, so we started with a weak base. So the first thing I want you to notice is that pH is high to begin. Then you've got this real slow kind of decline here. That's that region of maximum buffering. Well, I don't think the table's going to let me do it. There it goes. No, it's not. If I could smush this together, I'm looking for kind of the middle of the real sharp change in pH right there. That's our equivalence point, and if you check that out, it's at a pH that's below 7, which makes sense when you have a strong acid. Well, I can't draw it there, so I won't draw the muscle arm for you. And then here, down at the bottom of the curve, this is where the strong acid is predominating, and so that's why we have a lower pH here. Okay, now what I want to do is I want to get back and I want to show you some good graphs. So here you can compare. This is a strong acid with a strong base. So this is what I was talking about in the previous video, where this part of the curve is real steep in terms of slope. And you can tell it's strong because here's your equivalence point, and the pH at the equivalence point is 7. You know you started with an acid because you had low pH to start, and you are adding base. Okay, I know this graph is a weak acid, strong base, because the pH at the equivalence point, if I check out the steep part of the curve, and I go to the middle of it, right there, pH at the equivalence point is above 7, so I know the base is strong. This here is my region of maximum buffering, and this is where I have excess base. Okay, here's a graph that shows a comparison between the two of them. And the other thing you can notice is with a weak acid, the pH curve starts at a slightly higher pH. Now that really depends on concentration of the acid, but we're just talking about in general. Okay, so now I want to look at curves where we have a strong base. Starting with a strong base, I know that because we're starting at a high pH. Curve is real sharp, so I know it's a strong acid that is being added. If I look at the middle of this real sharp part of the curve, the middle is the equivalence point. That's at 7, so this is kind of screaming at me that this is a strong base, strong acid titration, as opposed to this one where I start with a high pH, so that tells me I've got a base that I am titrating with an acid because the pH ends up low. What I do here is I look at the real sharp part of the curve and I pick the middle, and the pH there is below 7, so I know we've got a weak base, strong acid. Here's my region of maximum buffering, and then here is where I've got excess acid. Okay, so what I want to look at here is choosing an indicator. You need to know approximately where your equivalence point is going to occur. And so what we want to do is we want to pick the indicator that's going to change color really close to the equivalence point. So if we look at this first one, phenolphthalein changes color right about here, and methyl red, the distinct color changes here, neither of which are close to that equivalence point. Now, if I look at this one, this equivalence point is a pH of 7. Of the two, phenolphthalein is probably a better pick. Here, the pH at the equivalence point is above 8, so this tells me it's a strong base. Lots of buffering here, weak acid. I want my indicator to change color really close to that equivalence point, so I'm picking phenolphthalein. Okay, now this next slide shows you the pH ranges for a bunch of indicators. And what it means, like for crystal violet, this is yellow and then green, and then this does not mean that it turns white. This is blue all the rest of this way. So like for, let's go to methyl red, because you did a lab with methyl red. It's going to change color kind of in right above 5, and it'll be yellow, totally yellow by the time you hit 6. So it's really changing from that kind of, I don't know, pinky color to yellow at about a pH of 5. So all of this is pinky orange, and then all of this is yellow. If you remember thymol blue from the lab, it had 2 points where it changed color because it had 2 protons to lose, so it was a polyprotic acid. This range was red, then you had a orange transition. This was all yellow, so that was the loss of the first proton. Then it turns kind of green, and then it went blue and darker blue. This was the loss of the second proton. So let's say you're doing a weak base strong acid. You know that the pH is going to change somewhere below 7. So you need something, you know, probably in this range. So you want something that's going to change color right there. So you just kind of look down and you see, okay, methyl red's probably a good pick for that. Maybe this bromocresol green. If I'm doing a weak acid, strong base, then I know that the pH is going to be above 7, you know, maybe in this 9-ish range. So I look down and, you know, phenolphthaleine's a good pick for that. If I need something about 10, thymolphthalein might be a good pick for that. So you can just use a table, a chart of indicators to choose the indicator that's going to change color. Really close to the equivalence point. And the point at which the indicator changes color is called the end point, because it's the end of your titration.